Okay, so we're just going to do a little more review of logarithms before we get into some more stuff. Hello. Yep. Okay, it is working. So what we've learned so far is that to take the derivative of the natural log, the answer is 1 over x. If we have the natural log of something other than just x, we use the chain rule. And the next thing is if we are given a natural log expression that involves multiplication and division, we use the properties of logarithms. So the first thing we need to do is just review on how you can simplify an expression. And you might think it's actually going the wrong direction, but it's not. A lot of times you want to combine stuff instead of taking it apart, but when it comes to taking derivatives, sometimes it's easier to do the derivatives if you decompose these. So the property of logarithms for products and differences is what you can do. So if you have a product of two numbers divided by a third number, you would rewrite this as the natural log of x plus the natural log of y minus the natural log of z. So whatever's in the numerator in the product you add together, and whatever's in the denominator you subtract. Another thing you can do with logarithms to simplify before you take the derivative is, in this case, you would rewrite the cube root as the third power. So if you have a power that's applied to the entire argument, or to the entire argument of the logarithm, you can take that outside of the logarithm. So this would be 1/3 the natural log of a squared plus 1. Now the thing is that I can't do anything further here because this squared is not applied to the entire expression. So I couldn't change this to 2 times the natural log of a plus 1. If it was a plus 1 squared, the quantity squared, then I could. But in this case, the squared is just on the a term. This one, what I would do is I would break it up into 2 parts. So I do the product first. So I'd take 3 times e squared. So you'd have the natural log of 3 plus the natural log of e squared. And then I would take the exponent out front. And then finally, the natural log of e is 1. So anytime you see the natural log of e, you can just replace that with 1. So this simplifies. First I do the product, change it into an addition. Then I take the exponent that's applied to the entire argument. I move that to the front. And then the natural log of e is 1. Here, what I would do is I would break it up and, again, use the product rule for logarithms. So it would be the natural log of z times, well, it's the natural log of z times this. So I would use the addition property. Well, yeah, the multiplication property, which results in an addition problem. So they're separated that way. And then finally, I would take the exponent out front and do that. And then if I wanted to take the derivative of these functions, it would be a lot easier because I don't have to use, if I have to use the chain rule, it's usually pretty simple. It's not complicated. Obviously, the derivative of the natural log of z would just be 1 over z. Here, if I took the derivative, it would be 2 times 1 over z minus 1. Instead of this original expression, which I'd have to use the product rule, the chain rule, all kinds of stuff. It would just be crazy. So we've looked at 2 out of the 3 ways of differentiating logarithms. The first one is just to use the chain rule. The second one is, well, we haven't actually used it yet, but we would use it to simplify things like that. And the third way is to do what's called logarithmic differentiation, which we haven't talked about at all, but we will. So I think we're going to look at each one of these, if I remember correctly. Well, there's nothing there, so it must be on the next page. Okay, so here's the first case. So it's the natural log of the sine of x. I can't use any of the properties of logarithms to simplify that. So I use the chain rule. So I would let f of u equal the natural log of u, and u of x equal the sine of x. So the derivative of the natural log of u is 1 over u. The derivative of the sine is the cosine. And then the chain rule says that f prime of x equals f prime of u times u prime of x. So we substitute in 1 over u for f prime of u and cosine of x for u prime of x. And finally we stick in u, which was the sine. So you get cosine of x. Well, let me not get ahead of myself here. So you'd have 1 over the sine of x. The sine of x is u times the cosine of x, which is the cotangent of x. So that's an example, another example of using the chain rule. If you have the natural log of something that isn't raised to a power, isn't multiplied, two terms multiplied together, it's just a simple chain rule type case. So why don't you guys try that one? Actually, I think we did it the other day, so hopefully you'll remember what we did. So u will be x squared plus 1, and f of u will be the natural log of u. And while you're doing that, I'm going to hand out something. U is the natural log of u, and u of x would be x squared plus 1. So the first part is the same, and the second part, you take the derivative of x squared plus 1, which would be 2x, and then you plug in to here. So that's your answer, 2x over x squared plus 1. Another way of thinking without using this expanded form is you could say, well, the derivative of the natural log is 1 over the argument, which would be 1 over x squared plus 1, and then you multiply it by the derivative of what's inside the argument, which is 2x. And so you could write that down, 2x over x squared plus 1. Let's skip that one for right now. Let's use the properties of logarithms. So we're going to both use the properties of logarithms, and then we're going to take the derivative. So before you take the derivative, use the properties of logarithms to rewrite this expression. If you can simplify it by using one of the three properties. In this case, you would rewrite this as the square root is to the 1/2 power, and then you could pull the exponent out front like that. And at that point, you can take the derivative. And if you look at, if I delete this page here, you can look at the previous example, and you can see they're pretty much the same after that. So you could probably figure what it is without even without going through this intermediate step. See if you can figure out what f prime of x is based on just looking at the similarities between the previous problem and the current problem. The only difference is you've got a half in front and you've got plus 4 there, right? So that's the answer. The reason you have x is because I've got the half factor. So a half times 2 is going to give you 1. And the denominator, instead of being x squared plus 1, is going to be x squared plus 4. Once you've simplified it to this point. Okay, let's look at a more complicated one. Yeah, here's another one. So in this case, there are absolute values, and you might wonder why the absolute values are in this problem and were not in the last problem. And one reason is because if you have the sine function, it goes positive and negative. So to make this function exist for all values of x, you have to, well, it's even going to have some vertical asymptotes at some point, because when the cosine of x is 1, you'll have 0 in the denominator. But otherwise, when you have cosine negative, you can, if you had negative cosine of the number being negative, then you couldn't take the natural log of it. So they're just extending the domain of the function. Let's actually see what this thing looks like, just out of curiosity. See if my graphing program can handle this or not. So if I did the natural log of the absolute value of cosine of x divided by cosine of x minus 1. Make sure I got enough parentheses here. One more. Oh, I didn't like that. Must not like absolute value. Let's see if I can find out what the terminology for absolute value is. And oh, here we go. Absolute value. That should have worked. Okay, let me just check it out here. The natural log of the absolute value of the cosine of x. I don't think I have to put this in parentheses, but I'll do it anyway. Okay. Let me count my parentheses here. 1, 2, 3. 1, 2, 3. Let's try that. Yeah, so that's what the function looks like. Okay, so the properties of logarithms, even with the absolute value there, what you can do is you can still rewrite it. So it would be the y is equal to the natural log of the absolute value of the cosine of x minus the natural log of the absolute value of the cosine of x minus 1. So that's using the properties of logarithms to simplify. And then to find the derivative, you would just take the derivative of these things, which we did it just a while ago. It would end up being 1 over the cosine of x. So and the question is, does it have to be absolute value? And I don't think it does. So I think we can remove the absolute value. So we take 1 over the argument times the derivative of the argument, which would be negative the sine of x. And then the second one would be the same kind of thing. We take 1 over the argument times the derivative of the argument, which again would be negative sine of x. So if I cleaned it up a little bit, I'd end up with negative the sine of x divided by the cosine of x. Negative times a negative is a positive. So I have the sine of x divided by the cosine of x minus 1. Again, we're using the properties of logarithms to take this quotient and make it into two parts that isn't a quotient. And this derivative is a lot easier than this derivative. Okay, the next thing is called logarithmic differentiation. And what that is for complicated products and quotients. And what we're going to do is we're going to take the natural log of both sides of the equation before we take the derivative. Because if you take the natural log of both sides, you're still maintaining the equality. But ultimately, we're going to take the derivative of the natural log of y, not the natural log of x. So the question is, how do you handle that particular derivative? So we're doing a little review of implicit differentiation, which we have to use in this case. So this is not implicit differentiation. This is just normal differentiation, because the variable in the thing I'm taking the derivative of is x. And I'm taking the derivative with respect to x. So the answer is 1 over x. Now, if I wanted to take the derivative of the natural log of y with respect to x, what I have to do with implicit differentiation, if you remember back to chapter 2, is you do the normal differentiation as if it was just a normal, if I was taking it with respect to y. So the derivative of the natural log of y is 1 over y, but because this variable here is different than that variable, I have to add my little dy dx at the end. Or I can put y prime, whichever one. So when I do this, I have an extra term. I have the y prime term. That's all we have to know for understanding what we're going to do next. So we're going to look at this this example, which is y is equal to x squared plus 2 over x. And we're going to do it a couple of different ways. We're going to use logarithmic differentiation first, just to show the process of how logarithmic differentiation works. And it probably is going to take longer to do it using logarithmic differentiation than it would be to use the quotient rule. I could use the quotient rule, or I could simplify it by dividing out and just using the rules for these two terms separately. But so in this case, it doesn't matter which way I do it. It's about the same level of difficulty. When you get to more complicated quotients, like the one, let me just go ahead and show you one that's more difficult. So like this expression. So y equals x squared times the square root of 3x minus 2 over x minus 1 squared. This one you have to use the product rule and the quotient rule and the chain rule and all kinds of stuff, and it would be very difficult to do it the other ways. But using logarithmic differentiation, this ends up being a lot easier. But for this one, like I said, it's going to be about the same level of difficulty either way we do it. Okay, so the first step in doing logarithmic differentiation is to take the logarithm of both sides of the expression. So our expression is this one. So if we take the natural log of the left-hand side, we get that. And if we take the natural log of the right-hand side, we get that. All we do is just put a natural log out in front of both sides. Now, before we take the derivative of each side, we're going to use the properties of logarithms to expand the right-hand side. So the left-hand side stays the same. But we can use the properties of logarithms, which says that that can be rewritten as the natural log of x squared plus 2 minus the natural log of x. So what this is doing is it's changing this quotient into a difference. Just like a slide rule changes a quotient into a difference. The next thing you do is you take the derivative of both sides. So the derivative of the natural log of y is 1 over y, but because it is implicit differentiation, I have to multiply by y prime. We saw that just 2 slides ago here. The derivative of the natural log of y is 1 over y times y prime. And that's always the case. Then the derivative of these, we just did something like this, so I'm going to write it out. The answer, the derivative of x squared plus 2 is going to be 1 over x squared plus 2 times 2x. So I take 1 over the argument times the derivative of the argument. And then the second one is the derivative of the natural log of x, just 1 over x. So that's the derivative. So this is implicit because I'm taking the derivative of some function of y with respect to x. The right-hand side, I'm taking the derivative of some function that's a function of x with respect to x, so I just use the normal differentiation. I use the chain rule here. I just use the formula there. Okay, next thing you do is you simplify the right-hand side. So what that typically means is you find a common denominator. So let's just let's put the left-hand side, just leave it the way it is, and let me just rewrite this. I'm not doing anything yet. I've just moved the 2x to the numerator. So the common denominator would be x squared plus 2 times x. So we would take the first term and multiply by the denominator in the second term, so we multiply by x and we divide by x. The second term we're going to multiply and divide by the denominator over here. So now we have a common denominator, which is going to be x times x squared plus 2. And in the numerator, we'll have 2x times x, which is 2x squared. And then we'll subtract x squared plus 2. Except I need another negative sign there because I need to apply that to both terms. So it'll be minus x squared minus 2. And then we combine like terms, so we'll get x squared minus 2 divided by x times x squared plus 2. So that's the right-hand side simplified. The next step, the fifth step, is to multiply both sides by y. What I'm trying to do here is solve for y prime. So if I multiply both sides by y, this is going to go to 1. And so I'll have x squared minus 2 divided by x times x squared plus 2 times y. The problem with this equation is that the right-hand side, the equation for the derivative involves both x and y. So I need to get it in terms of x. So what I do is I go back to my original equation and I find out what y was. So y was equal to x squared plus 2 over x. Okay, so let me write that down. X squared plus 2x over x. So that was my original expression. So then I plug that in here. So I get y prime is equal to x squared minus 2 over x times x squared plus 2 times x squared plus 2 divided by x. And then I simplify. So you can see I'll get x squared this is going to cancel out with that. So I get y prime is equal to x squared minus 2 over x squared, which is 1 minus 2 over x squared. So that's just two ways of writing the answer. Now, we're just going to do it the normal way. So what I've done is, here's the other way, and we're going to prove we get the same answer. So here I have my quotient, but I can rewrite that just like I do sometimes. I say, okay, I don't need to use the quotient rule. I can divide this by x and that by x to get that. And if I rewrite the second term as 2 times x to the minus 1 power, I can then take, and that shouldn't be 1, it should be x, sorry. Got ahead of myself. So if I take the derivative y prime, the derivative of x is 1. The derivative here is going to be plus 2 times negative 1, the exponent, times x to the minus 2 power, which is 1 plus, or actually minus 2 because of the negative sign. So that becomes negative 2 divided by x squared. And there you go. It's the same answer. And I could use the quotient rule as well, and I get the same answer. So obviously, in this case, logarithmic differentiation is a lot more complicated because I could have simplified it and just done a pretty simple derivative. But if I look at the next problem as an example, that's not going to be so easy doing it the normal way. So let me just go through the steps again. So step number 1 is, what's step number 1? Make sure I get these right. Take the natural log of both sides. Okay, so the natural log of y is equal to the natural log of x squared times the square root of 3x minus 2 divided by x minus 1 squared. And this natural log applies to the whole thing here. So I shouldn't have that extra little bit hanging out here. Step 2 is to use the properties of logarithms on the right-hand side. So what I can do is you end up with the natural log of x squared plus the natural log of the square root of 3x minus 2 minus the natural log of x minus 1 squared. Okay, so that's taking the natural log of both sides. Actually using the properties of logarithms. Now, I can simplify this by, let's go back, maybe I need to include this all in one step here. Use the property of logarithms. Okay, so that's not step 3 yet. We're still on step 2. So we've got to keep going a little bit on the right-hand side. So the natural log of x squared is 2 times the natural log of x. This is 1/2 times the natural log of 3x minus 2. And the third term is negative 2 times the natural log of x minus 1. So now I'm finished. I've broken them apart, so the product and quotients have become addition and subtractions, and the exponents have become constants out front. Okay, step number 3 is to take the derivative. So the derivative of the left-hand side is 1 over y times y prime. The derivative of the natural log of x is 1 over x. The derivative of 3 times the natural log of 3x minus 2 is 1 over 3x minus 2 times the derivative of this, which is 3. And then I have a last term, which is negative 2 times 1 over x minus 1 times the derivative of this, but that's just 1. So let's clean it up a little bit. Oh, sorry. Wrong equations there. So we get 1 over y times y prime is equal to 2 over x plus 3 over 2 times 3x minus 2. So this comes to the top. I just combine these two together, minus 2 over x minus 1. Okay, so that's the derivative. That was step 3. What was step 4? Simplify the right-hand side. Okay. So to simplify the right-hand side, we have to find a common denominator. So we'll have 2 over x times 2 times 3x minus 2 times x minus 1, all divided by 2 times 3x minus 2 times x minus 1. So what I've done is I've taken the first term and multiplied by the denominator in the second and third terms. Then I have the second term, which would be 3 over 2, sorry. The second term is 3 divided by 2 times 3x minus 2, and then multiplied by the other two denominators, like that. And then the final term is negative 2 over x minus 1 times the other two denominators, which is x times 3x minus 2 over x times 3x minus 2. So continuing on here, now we're going to have a common denominator, which is going to be x times 3x minus 2 times x minus 1. And the first part will have 4 times 3x minus 2 times x minus 1 from here. And I forgot a 2 right here, didn't I? So there's also a 2. So it's 2x, 3x minus 2, or x minus 1. Okay, then you have the second term, which is going to be 3 times x minus 1. That's that term. And then you're going to have 2 times x times 3x minus 2. So we need to multiply all this stuff out and simplify. So keep an eye on me, make sure I'm doing this right. So I'm going to use FOIL to do this. So I'll get 3x squared minus 2x minus 3x, so that's minus 5x, plus 2. 3x squared, negative 2x, negative 3x, negative 5x, plus 2. Okay. The next one will be 3 times x squared minus x. And then the final one will be 2 times 3x squared minus 2x. And that's all over 2x times 3x minus 2 times x minus 1. So go ahead and multiply out now. So we'll have 12x squared minus 20x plus 8 plus 3x squared minus 3x minus 6x squared plus 4x. So that's each one of these terms. 12x squared, negative 20, plus 8, plus 3, minus 6, plus 4. All over 2x times 3x minus 2 times x minus 1. So we'll have 12x squared plus 3 is 15. 15 minus 6 is 9. So we get 9x squared. We have 20x minus 3x. Negative 20x minus 3x is negative 23. Plus 4 is negative 19. And then we have 8 plus 8. Let's check that again. 12, 15, 9. Negative 20, negative 23, negative 19, 8. Okay, that whole thing divided by 2x times 3x minus 2 times x minus 1. Okay, and that's equal to 1 1 over y times y prime. And then finally, what we do is we multiply both sides by y. So we get y prime is equal to this whole big thing, 9x squared minus 19x plus 8 divided by 2x times 3x minus 2 times x minus 1, the whole thing times y. And then we go back and figure out what y is. So let's go back to the beginning. So y was this. Okay, paste. Okay, so there's y. I'm going to erase that. I'm going to take this. Actually, what I'm going to do is, I'm going to clone that. I'm trying to write as little as possible. So that goes to delete, and this gets deleted, and this gets pulled down, and you get that. Okay. So if you multiply by y with the y substituted, you get that expression. And then you can simplify because these cancel out with one of these. So let's see what we get. We'll get 9x squared minus 19x plus 8. So this is going to cancel out with one of those. So we're still left with x. And then in the denominator, we have 2. But the square root of 3x minus 2 divided by the square root of 3x, the square root of 3x2 divided by 3x minus 2 is the square root of 3x minus 2. And then I have x minus 1 times x minus 1 squared, so I'll have x minus 1 cubed. So that times that gives me that. And there's my final answer. Okay. So you're like, well, that still was a lot of work. Yeah, it is. It's a lot of work. But we spent most of our time not worrying about derivatives and just worrying about algebra. Okay, so that was pretty complicated, I must admit. So I'll let you finish copying that down. Hopefully I did it right. I'll check. There's a lot of places you can make a mistake in there. I was just thinking, hey Evan, if you can find a mistake, I'll give you 3 points. Not just kidding. Not just kidding. Did he just admit to what he did yesterday? Yeah, we got a little competition going here. Okay, so let's look at our handout now. So we're actually not going to take the derivatives of these. We're just going to figure out which of the three. Actually, I give you 5 choices, but really there's only 3 choices that end up being. 2 of them are wrong. Okay, if you choose to use the product rule, you probably are not doing it correctly. Okay, or if you're using the quotient rule. So if you see a product, you probably want to use the properties of logarithms somehow or another. So the way you look at these, so you're going to put down either A, D, or E. If you put down B or C, you've not been listening to me. And you ask the question, first, does the original expression not involve the logarithm? If the original expression does not involve the logarithm and there are products or quotients, then you want to use logarithmic differentiation like we just did. So for example, the first one, there's no logarithm in the original function, so we would use logarithmic differentiation to change that product into something simpler to do. If you do have the logarithm, if you can use the properties of logarithms to simplify it, then you want to use that. So for example, The second one, the natural log of x squared, I could just use a, the chain rule, but it would be easier to rewrite that as 2 times the natural log of x. So we'll go through first and identify which one of the three, A, B, or E, that we would use. And if there's no way that you can simplify the argument of the logarithm, then you're just going to have to use the chain rule. So just put A, B, or A, D, or E next to each one of these examples. Oh, actually, there is the case where you would just use the product or quotient rule. Okay. Sorry, that's on the second page. Okay, so let's do the first 2 pages. You might not be finished, but let's go ahead and review, and then we'll do the rest of them on Friday. So, what do we think here? What letter? What'd you got? D or E? D. Why might I say it's E? Okay. Yeah. Okay, so it's E because it doesn't involve the natural log initially. So what we would do is we take the natural log of both sides, and then we could rewrite the right-hand side as the natural log of x plus 1/2 the natural log of x squared minus 1. So that would be the simplification. Okay. Okay, the second one, that one is D, right? So you can use the properties of logarithms to rewrite this as that. The same with the third one, because you've got the square root. So you would rewrite that as to the 1/2 power. So that would become y equals 1/2 the natural log of x squared minus 4. This one's a little tricky because you could use the properties of logarithms. You'd have the natural log of 2 times the natural log of x. Ultimately, you'd have to use the chain rule. So if we took the derivative of this, we'd have 1 over 2 times the natural log of x times the derivative of this, which would be 2 times 1 over x. So that would be the derivative. So this part's the chain rule. So you take 1 over the argument times the derivative of the argument, which is 2 times the derivative of the natural log of x. Okay, so that's that one. This one is D because you can change the quotient into a subtraction and the square root into a power. So the way this thing would be rewritten is 1/2 the natural log of x plus 4 plus x squared. That's this part. So rewrite that as a 1/2 power, take it outside, and then you'd subtract the denominator. So I'm using the properties of logarithms to simplify This one is just C. And the reason is, yeah, we do have a quotient, but we just have the natural log of t, so we can't use the properties of logarithms. And we wouldn't want to take the logarithm of a logarithm. So it's just a simple, even though it involves logarithms, it's just a simple quotient rule problem. And the same way with the next one. It's just a quotient, it's a product rule. So this one is actually B. So this would be f of x and this would be g of x, and you would use the product rule. And then this one would be E, because I don't have a logarithm, but I can use the properties of logarithms to simplify the right-hand side. So what you would have is the natural log of x plus 3/2 times the natural log of x minus 1. So what you do is this would be added because it's in the numerator, but you could take the exponent out, and then you would subtract this one, and you'd raise this to the half power, but you could pull that half out front. So you'd have 1/2 times the natural log of x plus 1. So that would be the simplified version, using the properties of taking the logarithm and then using the properties of logarithms. Okay, so continue on now until 9.